everyone. In the previous lecture, we discussed the projectile motion, that is, the motion of a particle when it is projected at an angle of theta with the horizontal. We derived certain formulae which were related with this kind of motion. Then we derived for the time of light, that is the time that the particle takes to complete the projectile, that is, when it lands on the ground, so the total time that particle is taking. Then we derived the horizontal range, that is the x coordinate of the point when the particle is landing on the ground. And we also found out the maximum height till which the particle will go. Before that, we also derived the equation of the projectile, and we concluded that if the air resistance is neglected, the motion of the projectile is a parabola of the form y equals to ax square plus bx. Then I also gave you all a homework assignment of deriving the range of the projectile on an inclined plane. So first today we will discuss that problem, and then we will move on to the uniform motion, which is the last topic for this motion in a plane chapter. First, let's see the projectile on an inclined plane. So first, let's draw the diagram, because that's the first thing that we should always do in these kind of problems. So let's suppose this is the ground. This inclined plane is at an angle of theta, and the particle is projected at an angle of alpha above, like from this inclined surface. The initial velocity vector is at an angle of alpha. Let this point be A, this be B. So what we will do in this kind of problems is generally we always use our coordinate frame as this is the x-axis and this is the y-axis. Here also we can do the same, but that will make our problem a bit complex. So for making the problem simple, what we will do here is we will rotate the coordinate frame. That is, if this is x and y, what are we considering? That we will rotate it by some angle. That is, now this becomes x and this becomes y. But these x and y axes, they will be orthogonal to each other. That is, orthogonal means that we discussed this. The angle between them is 90 degree always. So this will still be 90 degrees. So as our inclined plane is at an angle of theta, so what we will do is we will take our axis, that we will rotate our coordinate frame also at an angle of theta. In this way, that is uh, x lies on the surface of the projectile, that is, it is pointing along the surface AB, and y is perpendicular to this surface, this inclined surface. So if we say this is the y-axis, it is perpendicular to this inclined plane, and this is the x-axis. So as we have now defined our coordinate frames, the first thing we will do is, as always, first we will write down what is given to us. So what is given is, in projectile motion, generally the velocity and the angle that the projectile, the particle is making at an angle with the horizontal, that is given to us. So it is alpha here. So what we will do is, we'll write ux, uy is u sine of alpha. Notice here that if we would have taken this axis, then the total angle total angle that the particle is making with the horizontal, that would be alpha plus theta. But because we have rotated our coordinate axis, the angle is still alpha. So here that will be cos alpha and uy will be u sine alpha. Similarly, we now come to our acceleration. Now here I would like to first draw this to make this concept clear. We know that g is like acceleration due to gravity is always pointing downwards. This is g, like in normal negative y direction. But here, because we have rotated the coordinate frame, the g vector will also, because g will not get rotated. No, g is always pointing downwards. But but its components that we are writing in the x and y direction, that will get rotated. So how we will write is like if we make a triangle, suppose this is the triangle and this is the inclined surface only which we are making here. This is theta, and if suppose G is pointing in this direction, this is G, and we want to resolve it along the x and the y axis. So what are our x and the y axis? It is this, like we have to extend this surface, no? So this is the x axis for now and the new y axis. So if we want to resolve this G vector into the x and the y axis, then we will say we will draw one component as here and the another component here. So as this angle is theta, this angle will also be theta, and because this is G and this is theta, so this component will come out to be G cos theta, and similarly this x component will come out to be G sin theta. This is nothing. I have just extended this x and the y axis in the negative directions so that we can easily resolve the vector G. And so now we can easily write acceleration also in terms of G. So our new acceleration here, because we say that our x-axis is pointing in this direction, but our G vector, that is G sin theta vector, is pointing here in the opposite direction. So we will take AX as minus G sin theta. Similarly, AY as minus G cos theta. So, and we also know here that this point from point A to B, like this is the horizontal range for the particle, because the particle, what is horizontal range that we discussed in the previous lecture? It was just the x coordinate, that the particle will x coordinate of the particle when the particle reaches the ground. So basically, when it crosses the y-axis. So here we have rotated frames. So here the y-axis is this. Y-axis is this, and when it crosses this x-axis, this point, which is said to be B, then AB is the horizontal range. That is when the particle is crossing the x-axis where y gets 0. So the horizontal range are here in this diagram, it is AB, that is where y coordinate of the particle becomes 0. So now we are going to derive this. So we'll again start with the most basic equations that we had derived earlier. Suppose this is D is the displacement, ut plus half at square. So for the, if we write this equation for the y direction, we will get y is equal to u in the y direction is uy is u sine alpha. And for the case of horizontal range, we see we had discussed the concept of time of flight that was denoted by capital T. So here we will get T, and acceleration AY is minus G cos of theta. So here we will get minus G cos of theta and again capital T square. And we know that this Y is 0 here. So we will keep Y is equals to 0, and then we will get u sine alpha into T, which is equals to half G cos theta into T square. This T and this T will cancel, so we are left with capital T as 2u sine alpha and divided by G cos theta. So this is basically what we have derived is time of flight. And now what we will do is, because we know the time that the particle takes to reach this point B, that is capital T, we will again use the same equation but for the x direction. and we will calculate the value of x coordinate at this particular time, capital T. So let's do this. Let me erase this first. So now what we will do is we will again start with the that x equation. X equation is x is equals to ut, so it is ux. Ux is basically u cos of theta into the capital T minus half. Acceleration is minus g sine theta. So that's minus g and again t square. But here, as x coordinate is given the name horizontal range, so we will write capital R over here. Now, what we had derived earlier was that t is equals to 2u sine alpha g cos theta. So now we will put this value of t here. So our R value becomes u cos theta, 2u sine alpha, and then t square. Now, as we know that from trigonometric relations, we know that 2 sine alpha cos alpha is denoted as sine 2 alpha. So here we will put the value here. We can see that this is 2. I'm sorry, actually that is why what I was thinking is I had written this wrong. So here it must be alpha. So now we see that this cos theta and cos theta cancels out. And when we use this property, so we can see it is 2 sine alpha and this one is cos alpha and this is cos theta. So we will get here u square 2 sine alpha and cos alpha becomes sine 2 alpha divided by g cos of theta minus half g sine theta. What we will do is we will take u square by g cos square theta common. And so when we do this, we are left with sine 2 alpha over here and we will multiply 1 cos theta here. And then again, j cos square theta has been taken out and we are left with sine theta and sine alpha over here. This 1, 2 and 2 will cancel out and 1, 2 will be left. And again, we are left with this sine theta and here we are left with sine square alpha. Now there is also one identity in trigonometry which is 2 sine square alpha can be broken down into 1 minus cos 2 alpha. So when we broke this down, like where we are writing this 2 sine square alpha, so we will get, so this is what we get over here. And again, there is an identity in trigonometry that is sine 2 alpha and cos theta, that is this term, and the sine theta and cos 2 alpha. When we will add both these terms, we will get sine 2 alpha plus theta. So when we write this in simpler terms, we will get u square by g cos square theta sine 2 alpha plus theta. This is on combining this term and this term. And here we have minus sine theta term is left out. So this is the formula for the horizontal range. You cannot simplify it further. I mean, this is the last step. So this is the formula for the horizontal range of the projectile. That is, this is AB. We have also find out the capital T, that is the time of light over here. If you want, you can also derive the this time of maximum height yourself. And now we will move on to the uniform circular motion. So what is uniform circular motion? Whenever an object follows a circular path at a constant speed, the motion of that object is said to be uniform circular motion. This word uniform here simply means that we are talking about the speed which is kept constant. Uniform means constant. Sorry. But a key point here we have to note is that as the object moves in a circle of radius r, its direction is keep on changing, and so does its velocity. We had seen the difference between the speed and the velocity. That is, in uniform circular motion, suppose a particle is moving in a circle. So we say that even if the speed is kept constant, but the direction of this, the particle will keep on changing. Sometimes it would be this, sometimes it would be this, sometimes it would be this, sometimes this. So when we are talking about velocity, the magnitude of velocity is always constant, but the direction of the velocity vector keeps on changing. That is why we say that here the velocity vector is not a constant vector. And so if velocity is not constant, it will also have some acceleration associated with it due to this changing velocity vector. So now we are going to first find out the magnitude and the direction of this acceleration in the constant in the uniform circular motion. So first let's draw it. This is the center of that circle. And suppose the particle is moving this way, like from here to here. And at some time t, the particle is over here at p. And at another time, the particle is here at p dash. So the displacement vector here would be this. So let's say that the position vector of the particle when it is at p is r. This is the position vector r. When it is at p prime, the position vector is r prime. Also, we say we will define the velocity vector over here. As we know that the velocity is always kept along the tangent at that point in the direction of motion. That is, as the particle is moving in this direction, the velocity vector will be somewhat in the direction of the tangent. This is the velocity vector v. And similarly, here if we say the velocity vector will be in somewhat this direction, that is v dash. So now we have drawn the velocity vectors and the position vectors. Now we can use the triangle of addition that we discussed previously in drawing the delta v, that is the change in the velocity vector. So as we see that delta v would be v dash minus v. So v dash is this plus of minus v. So because v is here, so minus v would be here. Sorry, we are not drawing the parallelogram law. We are using the triangle law. So we will write it this way. Let me erase this first. So and when we join these two, we get this is v. We get this delta v. So this delta v vector um, is perpendicular to the delta r vector, because as we can see in this diagram that this position vector is always perpendicular to the velocity vector. This r is perpendicular to v. This r prime is perpendicular to v prime, because v is always drawn as a tangent to this point. So they are always perpendicular. So we can say that delta r is perpendicular to delta v. We can say it this way also. Now, as we know that the average acceleration is written as delta v by delta t. So the direction of average acceleration will be in direction of delta v. So as delta v is perpendicular to delta r, we can simply say that acceleration is also perpendicular to delta r. Now you must notice here that if we place this delta v vector on the line that bisects the angle theta, this is say angle theta, or you can call it delta theta. There is this line which is bisecting this angle, and when we place this velocity vector over here, that is delta v vector over here, what we notice is that this vector is pointing towards the center of the circle. And when we keep on decreasing the delta t, that is we are talking that is we are going from average acceleration to instantaneous acceleration. That is, as delta t is tending towards 0, we know that average acceleration will go to instantaneous acceleration. So we say that that is why the instantaneous acceleration of a particle is always pointed towards the center of the circle. In the case of uniform circular motion, whenever if the particle is over here, the instantaneous acceleration would be pointing towards this way, that is towards the center. If the particle is here, it will point towards the center. If the particle is here, it will point towards the towards the center. So this is what we have derived, the direction of the acceleration. Now for calculating the magnitude of the acceleration, what we will do is, let's write A. Here we are talking about the instantaneous acceleration because average we don't need, because generally uh, for the practical purposes we only need the instantaneous acceleration. So here that's why we are taking delta V by delta T, what the magnitude of delta V here and the magnitude of acceleration here. Now if we draw a triangle using the velocity vectors this way, this is the velocity vector V and V dash is here. So V dash is here and delta V vector is here as we draw it here. So and we name this triangle as GHI. We can compare these two triangles. That is the one which we have drawn. This is the center C. So this triangle CTT dash is one triangle that we have drawn using R and R dash. And this another triangle is GHI that we have drawn using V and V dash. That is as the velocity vectors. And this is delta V. So we can say that as we have written here that delta R is perpendicular to delta V. That is, if R and R dash, they make an angle of delta theta, then obviously V and V dash will also make an angle of delta theta here. And so we can say that these two triangles are similar. So we have also studied the properties of the similar triangles. So using the properties of similar triangles, we can write delta V by V is delta R by capital R. Here V is the magnitude of the velocity and here R is the magnitude of the position vector, that is, this is the radius of the circle R, and here V is the magnitude of velocity. And this V and R are both constant values because as we had seen, no, that the magnitude of the velocity is a constant, only its direction is changing. So this magnitude is what we are talking about. Now from here we can write mod of delta V as V mod of delta R by R. As we had seen here that acceleration, this limiting that delta t tending to 0 is delta V by delta t. So here what we can do is we can put this value of delta V, the mod of delta V. So this value we will put it over here. So what we will get is, let's erase it for now. When we will put this value and we will put the limit delta t tending towards 0 and delta V mod is given by V mod of delta R by R, and we will put delta t from here. This is delta t. And as V and R are constant values, so we will take these out. V and R, we take these out. Then we will again put the limit over mod of delta R, mod of and delta t. So also if we say that we keep on reducing this P dash, I mean if this P dash, we have taken these 2 points who are far away from each other, but if we keep on reducing this the distance between P dash for delta t tending to 0. So we can simply say for delta t tending to 0, we can say that mod of delta R can be approximated as v delta t. What is this? This is speed is equals to distance upon time, nothing else. But the only thing here, the thing to notice is that this is for delta t tending to 0. This is not a general expression. This will hold only when we are talking about very small time, and therefore this expression can be approximated as this. So again, in this expression for acceleration, what we had written is v by r limit delta t tending to 0 mod of delta r by delta t. We will put this value over here, v by r, and delta r by delta t is v. So again, we will get is v square by r. So this is the result of the magnitude of acceleration that a particle is that the particle has an acceleration when it is moving in a uniform circular motion. Now you should also know that this acceleration is called the centripetal acceleration. This is the centripetal acceleration, and this is not a constant vector because its magnitude is constant. That is always v square by r, because the magnitude v, that this velocity v is a constant, and r is also a constant. That's the radius of the circle. So the magnitude of the acceleration is a constant thing, but its direction is continuously changing, as we had derived earlier that the direction of the centripetal acceleration is always towards the center of the circle. So this is not a constant vector. Now we will also look at the concept of angular speed over here. As we saw in the previous diagram, that the angle theta, that was the angle between the two vectors p and p dash, was angle theta, was delta theta. So delta theta is sometimes, not sometimes, it's called as angular distance, because it's basically it tells us about the distance that the particle has traveled in the terms of angle, that how much angle it has covered when it has gone from p to p dash. So that's why it is known as angular distance. So as we know that speed is equals to distance upon time. So when we convert it into angular form in angular terms, we can write angular speed is equal to angular distance upon time taken. So this is the angular distance, delta theta, and this omega is said to be the angular speed. Also, we had seen for that velocity, if the two vectors were, this was the vector for p dash point, and this was the vector for p point, and they had an angle of delta theta between them, and this was the circle. But for delta t tending to 0, what we will draw is that its distance is the angle between them is very small. So I mean, this is p dash, this is p, this is the angle between them. So we can say that the distance between them, that is p dash here, you can see is p dash, and here it is, let's say p dash as delta s. So here for delta theta, which is very small, which is tending to 0, you can say that this arc, this length of the arc, it can be reduced to this pp dash vector, this pp dash distance. So for this limiting case, these two lengths, they are equal, they are assumed to be equal, and so we can write that velocity v is equals to delta s. Sorry, let me write it properly. Velocity is change in the displacement. Velocity is the displacement with respect to the time taken. So that's delta s by delta t. But for the limiting case, we have seen that delta s, it is equal to r, that is r into delta theta. That is, this length, this arc length is equal to the radius of the circle into the angle that arc is covering. So this is a standard formula in mathematics. This is nothing new. This is a standard formula. but we are using it here only for this limiting case because we are interested in the instantaneous acceleration. We are interested in the instantaneous angular speed. That's why. So when we put this value of delta s, it will become r delta theta by delta t. And from here we had previously we had seen that delta theta by delta t was called to be as angular speed. So we can call it as r omega. This w is known as omega. That is the symbol for the angular speed. It is used everywhere. And so acceleration, which was equal to v square by r, you can put it simply here, r square omega square divided by r. This r will cancel out. And acceleration in terms of angular speed, we can write it as omega square r. This v is actually the linear speed. That is in terms of the distance or the displacement. And here omega is the angular speed. That is in terms of the angle that the particle is covering in the while it is in motion in a uniform circular motion. Also, I would like to tell this time period, which is denoted as capital T. That is the time that the particle is taking to complete one full revolution of the circle. That is when the particle starts from here and it covers one full circle, one full revolution, and comes back to its original point. The time that the particle is taking for this one circle is known as time period. And other thing is that for the number of revolutions that the particle makes in 1 second is called to be the frequency. We will denote frequency with this symbol. The symbol is called eta, and that is equal to 1 upon time. This is time period, 1 upon time period. So basically this frequency tells us that how many number of revolutions that the particle has made in 1 second. So if we talk about in terms of this frequency and time period, we can simply write that this for this capital T, for one circle, for one complete revolution, this is the circumference of the circle. So the distance, that is, let that distance be total distance be s that the particle covers is 2 pi r, and the velocity will be this distance upon time period that it is taking is capital T, and then we can write it as 2 pi r into 1 by t. 1 by t here can be written as frequency. This is frequency, so it is 2 pi r eta. It's writing velocity in terms of frequency. Also, the angular speed omega can be written as 2 pi by t, or again in terms of frequency if we write, it is 2 pi eta. Also, acceleration, which is v square by r, it comes out to be 4 pi square eta square r in terms of eta. So here we have written down the distance. The distance is actually the circumference, but we have written down this velocity, this angular speed, and the acceleration in terms of this frequency eta. Now we'll do one question to actually understand this concept of time period and frequency. So suppose the question says that an insect is trapped in a circular groove. The circular groove is, this is some kind of circular groove, and the insect is trapped inside this groove. That is, it can only move inside the groove, and it moves in a circle of radius 12 centimeter. The radius of that groove 12 centimeter, and it completes 7 revolutions in 100 seconds. That is, it moves 7 times around this circle in 100 seconds. The total time is 100 seconds. And what the question is asking is, what is the angular speed, that is omega, and the linear speed, that is velocity, of the insect and also find out the acceleration. So we have been given that it completes 7 revolutions in 100 seconds. So it's basically the frequency, the time period is defined at the time that the particle is taking to complete one revolution. So basically, if the particle is taking 7 revolutions, it takes 100 seconds. So obviously for one revolution, unitary method, for one revolution, it must have taken 100 by 7 seconds. So for one revolution, the time taken is said to be the time period, that is capital T. And therefore, eta, that is the frequency, is 1 by T, which is 7 by 100. Now what we see is the angular speed. We just derived it, that is written as 2 pi by T or 2 pi eta. So here we will write 2 pi by T as 7 by 100. And on putting the values here, we will get 0.44 radians per second. So radians here is the unit, radians per second is the unit that we use to define this omega, that is the angular speed. So radians is for the unit which is used to define for the angles. So as if when we write velocity, we write it in meter per second because this is the length the particle is traveling. And when we take out this angular speed, it is in terms of angles. So for omega, we use the unit 2.3 centimeter per second square. So this was the last topic that we had to discuss in a chapter, motion in a plane. And we will now end this chapter.